So welcome back. Again, not everybody's here yet, but I'm sure more people will show up. Um, we're working our way through chapter 5, the biggest chapter. We have a couple of weeks of classes left, 2.5 maybe, almost 3 weeks. So we should be able to finish chapter 5 and 6. Chapter 6, very, very short chapter. So kind of like chapter 4, should only take us a class or two. Okay, so yesterday, sorry, obviously Thursday, not yesterday, but Thursday, we looked at the composition of petroleum and natural gas. And really the answer here is there is no set composition. It's mostly carbon and hydrogen, and by far mostly carbon. And then there's other trace amounts of things like nitrogen, oxygen, sulfur, and metals. And that's really all we can say. And the same thing goes for types of hydrocarbons. Most of them are naphthalene or alkanes, meaning straight chain hydrocarbons. Naphthalene would be alkenes from 5 to 10 hydrocarbon or carbon molecules. There's some aromatics, and then there's asphaltics, which are like very, very large, complex molecules. You don't need to remember any of these numbers or anything like that. Just know that, I mean, the composition of petroleum is obviously mostly carbon, and it varies from place to place. Okay, we looked at this in great detail yesterday on Thursday, and then I stopped there. So what I would like to do today is to discuss some of the non-carbon compounds that you might find in petroleum, or crude oil is what I guess I should be saying. So what I mean is when you extract crude oil from in its natural form from under the Earth's surface, under sedimentary rock, what are some other compounds that you might get? So we'll do nitrogen, sulfur, and oxygen. And that won't take us very long. And then, I'll get into this. This is, I think, my favorite section, 5.11 and 5.12. I love. Okay, so very quickly. Nitrogen, carbon dioxide, hydrogen sulfide are very, very common non-hydrogen parts of petroleum. Carbon dioxide, it's a quote toxic gas. Now, when I say carbon dioxide is toxic, I don't mean it will kill you. It's inside all of our bodies right now. But if you were in a room that was filling with carbon dioxide, like from a fire, that would be quite toxic to you because your body would breathe in the CO2 instead of O2, and you would not be very healthy. Nitrogen, typically a pretty safe compound by itself. Hydrogen sulfide, very common byproduct of crude oil refining and extraction, quite a toxic substance as well. So some of the non-carbon compounds like nitrogen, carbon dioxide, hydrogen sulfide, very, very common. So those are three you should know. You should remember that nitrogen, carbon, CO2, and H2S are very common. There are, however, other compounds involved. They can be very complex as well. So let's start with sulfur. Typically, sulfur is the largest group in petroleum, a non-hydrocarbon. So besides hydrogen and carbon, sulfur is typically the highest. It can be very low, though. It varies considerably, meaning some crude oil can have as low as 0.1%. Some places in the world, the crudes can be up to 5 to 7% sulfur. So, you don't have to remember these numbers. But one thing that's interesting is when sulfur increases in your crude oil, the amount of sulfur, the crude oil tends to become more dense. And that won't really affect you guys in this course. We'll talk a little bit about density later, but sulfur can increase the density. Sulfur compounds are also really bad for the refining process for your equipment because the sulfur can ruin. So when I say poison, I mean basically ruin the metallic catalysts used in refining. So we really want to get rid of sulfur oops, sorry guys, if we can in the refining process. Just give me 1 second here. Okay, sorry guys. The somebody was in my hallway and the dog doesn't like that. Oh, sorry. I just read in the chat too. Niam mentioned like people usually faint in a burning house. That's going back to the carbon dioxide talk. Um, that's why carbon dioxide is so scary because from people who've survived CO2 poisoning, they don't even know it's happening sometimes. You can just pass out. Your body just kind of puts you into sleep mode because you're not getting any oxygen to your brain. And if you fall asleep while your house is on fire, I mean that's not good. So, anyways, kind of interesting, kind of sad. So back to sulfur. Sulfur compounds, really bad. We want to get rid of sulfur in crude oil because it can ruin the catalyst used for refining. We use catalysts for alkylation and isomerization, platforming. We want to get rid of the sulfur. Most places in the world, definitely in the United States, in Qatar, in Canada, Japan, all these countries, there are legal limits on the amount of sulfur in most products, petroleum products or petrochemicals. So, anybody refining crude oil in the world, in the developed world, Middle East, North America, China, whatever, Russia, wherever, they would have limits on the sulfur in those compounds. So they need to be removed. We might talk a little bit about removing these compounds later, I think at the end of this chapter. So some examples of sulfur compounds, you don't need to memorize these. I have a suspicion that your final exam might be online. It might not be, we'll see. I would prefer it to be online for safety, but you don't need to memorize these. And especially if your exam is online, you can always use your notes. But common sulfur compounds, well, there's really one I would memorize. Hydrogen sulfide is very common. Other ones can include thiols. Thiols, remember, are a functional group that has S and H. So like an alcohol, but instead of OH, SH. Alkyl sulfides, this just means a carbon chain with a sulfur in it, or complex ring structures that have sulfur in it. So thiobenzene or methylbenzothiophene, some crazy name of compounds. They're very complex. The only sulfur compound I would worry about is hydrogen sulfide. All right, what about oxygens? Oxygens in crude oil are typically in ring form or aldehydes, alcohols, ketones. These are just some examples of oxygen compounds that you might find in crude oil. So we have phenol, or a benzene ring with an alcohol group. We have cyclohexanone, which is a ketone. Um, and then on the last one, we have a cyclohexane ring with an aldehyde on it. So these are just some examples. You do not need to memorize these, okay? Do not memorize. Okay, really the purpose of this is just to explain to you that crude oil isn't just carbon and hydrogen. There's lots of things in there. And specifically, wink, 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 you should remember things like sulfur can cause big problems because sulfur can really ruin your refining equipment. All right, oxygen compounds. In some oxygen compounds, you can have carboxylic groups. Now remember, carboxylic or is CO2, it can be acidic. A carboxylic acid, right, is an acidic compound. Acids can be also propose a problem in your refining process. Acids have been known to, in some cases, corrode metal or react with things. So the acid number of crude oil is how many milligrams of potassium hydroxide, a base, it takes to neutralize the carboxylic acid. You do not need to memorize this either. There's really nothing on this slide you need to memorize, but you should know that when testing crude oil, they look at the acidity of it, and the acidity is related to carboxylic acids. So crude oil can be acidic if there's a lot of carboxylic acids in it. I'm going a little quick because really, again, I'm not going to ask you to define or explain any of these compounds. Just know that these compounds are can hurt the purity of your product, can hurt your refining equipment, and typically they're removed. Acids can be neutralized with bases. Sulfur can be removed. We'll talk about that a little later in this course to protect your equipment. The last major type of compound are nitrogen. Very little is known about. Now, I did a lot of research on this. Like when I say little is known about the nitrogens in crude oil, um, it's not as deeply studied as say sulfur products, okay? But there are nitrogen compounds found in different parts of the world in crude oil. A lot of times they're in very complex rings. Obviously, you do not need to memorize this, okay? So don't worry about this for studying or anything. But nitrogen compounds found in crude oil can be very complex. And the last type of chemical you might find, so we did sulfur, oxygen, and nitrogen, are organometallic compounds. Now, these are crazy compounds. This is an organic molecule that typically surrounds a metallic element. So organometallic is the word, it's called a portmanteau. It's putting together two words, organic and metallic, organometallic. Typical organometallic compounds that you might find would include vanadium and nickel. They can be present in parts per million amount, so very small. And usually they're in oil soluble compounds called porphyrins, which you do not need to memorize this. But what's interesting about this chemical is it's very similar to the coloring matter, the chemicals that give blood and chlorophyll in plants color. So this would make sense if you think about where crude oil comes from, right? Decaying organic material deep under the Earth's surface. So plants and creatures that are under the Earth's surface under high temperature and pressure over lots and lots of time turn into crude oil. So it would make sense that we would find compounds similar to chlorophyll or blood, for example, in oil. All right, so you can probably hear my dog out there going crazy. I'll go get her in a minute. We are going to start section 5.11. Okay, so I'm just going to grab my puppy, bring him back inside. I'll be right back. All right, I am back. I had it was Niam brings up a good point. I had the back, I have a door that goes outside open, and she was barking at some creatures out there. So Niam mentions crude oil is black. Oh, definitely black. I mean, the complex mixture of hydrocarbons, nitrogen, sulfur, all these things. It is a black molecule. So I'm not saying like that this organometallic compound actually colors the oil. It's just found in oil, which would make sense because oil would be composed of decaying plant and animal matter. So the fact that there's chemicals similar to blood or chlorophyll, not the same chemicals, similar, would kind of make sense. But yeah, crude oil, definitely dark black, usually very viscous. If you're not familiar with the word viscous, it means like thickness, like honey is viscous, water is not. All right. So again, I went a little quick through that because that's not something I would ask you particularly on a test or anything. And I really wanted to get to this section. Section 5.11 and 5.12 are like my favorites by far. Sorry about my dog there. 5.11 covers the thermal properties of petroleum, and 5.12 would cover some different things like solutions and emulsions. So this is going to be a little boring, I will warn you. The topics it's very definition heavy. These are definitions you will be tested on your final exam, typically in a matching type of situation. So as always, you don't really need to write in-depth paragraphs or explanations. You just need a basic understanding of what these terms are. So we're going to look at the thermal properties of petroleum. Now, every single one of you have done Chemistry 1121, which means you've studied thermochemistry, and it's kind of the same idea. We're talking about kind of like heat properties of petroleum. So, first word, cloud point. A cloud point refers to okay, first let me interrupt myself. These words, these definitions, they are very self-explanatory, meaning the definition or term are very closely related. So when you hear the word cloud point, it is the point in which a chemical becomes cloudy. Okay, so what do I mean by cloudy? Cloudy means like you can't see through it. It would, like, you think about a precipitate in the lab. Cloudy is, I'm trying to, like, almost milky. It's not opaque. You can't see through it, or it is opaque. I never get that right. But cloudy, kind of like a precipitate forms. This happens at a certain temperature because when things get colder, they begin to solidify. So waxes in your petroleum products, typically in diesel, when it gets really cold, they start to solidify, which means you get a cloudy appearance. So that's it, cloud point. It's the point that, now when I say point, I mean the temperature at which something becomes cloudy. All right. So the problem with cloud point, there's a lot of problems here. One, if you lived in a very, very, very cold country, you might not be able to start your car if you were running like diesel fuel that had some impurities in it. If it was so cold, it would almost thicken to a point where you might not get your car to start or vehicle. The big problem in oil refining is, well, if you get to the cloud point of, say, crude oil, where the large number hydrocarbons begin to solidify, it can actually clog, fill pipes, plug them. So cloud point can mean that oils in cold temperatures plug filters or small holes and can cause big problems in oil and gas industry, in machinery, in equipment. So really the big takeaway from this is the cloud point is the temperature in which large hydrocarbons begin to solidify. And the reason it's called cloud point is because it would start to look cloudy. All right, what about pour point? Pour point, exactly what it sounds like. It's the point in which pouring, which deals with flow or viscosity, becomes affected. So the definition, pour point of a liquid is the temperature below where the liquid loses its flow characteristics. And this is very much related to viscosity. Sorry. Sorry about that. Just fixing my pen there. Viscosity is related to the flow of something. So the pour point is the temperature where the liquid will start to not flow. It becomes thick. So if you're trying to push oil or crude oil through a pipeline and it's so cold that it's not flowing very well, you could have big problems. In crude oil, a high pour point is usually associated with paraffin. So large wax materials, it can come from plant matter. And it's another problem. If you get too cold, it doesn't flow very well, and you can see problems in your pipelines. Congealing point, I'm sorry guys, this is pretty boring stuff. I'm just reading definitions to you, but these are important. I have a couple more definitions. I have a lot more definitions. I might not do them all today. Congealing point, well, exactly what it sounds like. It's the point, meaning temperature of a liquid, where something congeals. Now, you might not know the word congeal. It's not a word I use a lot. It's kind of a weird sounding word, but it means solidify. So if you've ever made like a curry or gravy, right? Like think about it, making a curry, gravy, some sort of food that's hot over the stove. It's, liquid form. But if you leave it out for a day or you put it in the refrigerator overnight, when you take it out the next day, it can be almost solid. And in the food world, we would say that it's congealed. Typically happens with high fat uh, food. So like curries and gravies that have a lot of fat in them, like butter or even like coconut cream. If it gets cold enough, it turns into solid. It congeals. So the congealing point is the same as the melting point. It's basically just a term that they would use in industry. Also, a huge problem for oil and gas, probably not in Qatar, but maybe northern Canada or northern Russia, where it's very cold. If your hydrocarbons get to the point where they congeal or become solid, they're not going to flow, meaning it could clog pipelines and cause big problems. Freezing point. I do apologize for all these definitions. It'll get a little bit more interesting tomorrow, I promise. Freezing point. All right. I mean, everybody knows that. We did that in chemistry 1120 in lab number 5, which I know you can all remember a couple years ago. We talked about freezing point in 1121. It's the temperature where a liquid becomes a solid, very similar to congealing point. These are all basically related. These are all related to the temperature and what happens as things get colder. When they get colder, they can become cloudy. They can start to pour or flow slower. They can congeal or freeze, meaning they become solid. All right, pretty straightforward. One interesting fact is that the freezing point can be lower than the melting point, which is opposite of what you guys learned in chemistry 1121 or 1120. In 1120, we were told that the freezing point and melting point are the same. Water freezes at 0 and it melts at 0. But when you're dealing with very complicated organic compounds like crude oil or fat mixtures, the freezing point can actually be a little bit lower. So it will freeze at, say, like minus 30, but it would melt at, say, minus 25. And you don't need to memorize that, but it is an interesting phenomenon. All right, now this is a cool definition. Volatility, what a cool word. Volatility, you guys, any of you gentlemen or ladies who wear cologne or perfume, you're wearing volatile chemicals on you all the time. That sounds real scary, doesn't it? But volatility literally just means that a substance has a tendency to vaporize. So when you say a chemical is volatile, you might think like dangerous, and not always the case. The reason in like industry we are careful with volatile substances is because when they turn into vapors, they can become easily ignited. So, when uh, ethane, propane, butane become gases and somebody decides to have a cigarette or light a lighter, big problems. But volatility in nature can be anything, like perfume. The reason when I walk by a student that has a lot of perfume or cologne, I can smell it, is because that cologne, when it hits your warm skin, it vaporizes. That's why when you wear cologne, you should put it on, like when you're testing it, you wear it on your skin, not your clothing, because the heat of your body vaporizes it, and that's what makes it kind of smell. Pretty interesting. Oh, sorry, I just poked my dog right in the eye. Whoops. Anyways, so at a given temperature and pressure, a substance that we would say is volatile is more likely to exist as a vapor. And again, for anybody here who's done like occupational health and safety or WHMIS, some volatile chemicals can propose a fire risk. Again, propane, butane, pentane, hexane, if they turn into vapors and there's a spark, big explosion, big problems. So this is kind of going back to the beginning of chapter 5. The knowledge of volatility is what helps us separate these mixtures, because we separate crude oil, like I told you a couple weeks ago, with distillation. And distillation follows this volatility concept. You heat up the oil till it turns into a vapor, and then we collect it. So volatility is directly related to distillation or separation. I almost said separation just then. Now, guys, this slide I don't really have to say much about because you know this. The crude oil flows into the distillation tower. It's heated up. The more volatile components, so methane, ethane, propane, butane, they will vaporize first. So the more volatile compounds have the lower boiling point. These vapors will move up the tower, hit a colder surface where they condense, and then we collect them. So hint, hint, wink, wink, the most volatile chemicals are at the top of the column. Most volatile meaning lowest boiling point. So if I asked you, wink, 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 nudge, 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 if, where are the most volatile compounds found in a fractional distillation column? Always at the top. The least volatile, the least likely to turn into vapor, they'd be at the bottom. That's your asphalt compounds, asphaltics, and your thick or oils like lubricants. They're typically at the bottom because they take a lot of heat to vaporize. All right. Well, how many more definitions do I? Well, we only have 3 more, so let's finish these definitions, and then tomorrow, or sorry, I guess I should say Wednesday, we will get into another really cool chapter, or section 5.12. So 3 more definitions, and I'm done. And I do apologize for this kind of boring class. Now, this definition we did in Chemistry 1120. I know you did because you wouldn't be able to talk about thermochemistry without talking about specific heat. Specific heat is the amount of heat per unit of mass required to raise the temperature of something 1 degree Celsius. What a crazy definition. The simple definition is it's how much energy something absorbs when you're heating it up. Heat capacities or specific heats are not the same in every compound. Water has a very high specific heat. It can absorb a lot of energy, but something like air, oxygen, carbon dioxide, nitrogen, has a low specific heat. So that's why you can like stick your hand into a 200 degrees Celsius oven and you're fine, because the air in that oven doesn't have a lot of energy, heat absorbed in it. If you tried to stick your hand in 200 degrees Celsius oil, you would lose your, you wouldn't lose your hand, but you'd lose the skin on your hand for sure. You'd have, first, second, third degree burns. So specific heat is related to how much heat something can absorb. And every chemical has its own specific heat. So Naim, I think you just wrote this. Does it have anything to do with temperature? Honestly, everything I've talked about today has to do with temperature. Remember that this section is the thermal properties of petroleum. So everything here is directly related to temperature. The way specific heat relates to temperature is that a chemical that undergoes a large temperature change would typically have a large specific heat. You do
I wrote
not.
something before that.
Sorry?
I wrote something before that.
Oh, you meant does volatility have to do with temperature?
No, I mean when you throw carbon dioxide through lime turns it cloudy. Lime water.
Um,
Then read the chat.
yeah, I can read the chat. Yes, no
Above
problem.
that, I wrote something
Yep. Um, I just have, does it have anything to do with temperature?
before that.
Makes it cloudy, carbon dioxide through lime water. I
Yeah,
don't, does what?
does it have anything to do with the uh, temperature? Like
Mm,
when you pass carbon dioxide through lime water?
mm, okay, so the question for everybody listening, there's only a few people here today. The question is, when you put carbon dioxide through lime water, what does it have to do with temperature? Really, the only answer I can give on that, and again, this is just coming from my chemistry background. I don't know much else about carbon dioxide through lime water, but gases are The solubility of gases are controlled by the temperature. So when you drink a really cold Pepsi or Coke, it burns because cold liquids can hold on to more gases. So cold drinks have more carbon dioxide than warm drinks. So when you're passing carbon dioxide through lime water, in cold lime water, you would be able to keep more carbon dioxide inside. Whereas if the lime water was hot or warm, a lot of that carbon dioxide would evaporate or I guess leave as a gas. That's about as much of detail as I know about that. Okay. So guys, specific heat, you definitely don't really, we're not getting into calculations in this course. This is from 1120. Just know that the specific heat is the relationship between heat and the temperature change of a substance. Some substances, when you heat them up, they go through great temperature changes. Some go through very small temperature changes. That's really all you need to know. Two more definitions, flash point and latent heat, and then I'm done. And I'll just very quickly go over these, and that's it. So latent, or sorry, flash point. The flash point is the lowest temperature at which vapors will ignite. So again, when you hear the word point in chemistry, it means temperature. So the temperature where a chemical will ignite at the lowest temperature where a chemical will ignite, meaning catch on fire, is called the flash point. This is very important for safety, right? Because if you have volatile hydrocarbons that are above their flash point, that means if there's an electrical spark, somebody lights a match or a lighter, it can ignite and cause an explosion or fire. So flash point is a term you might hear in safety, where it's related to the temperature, the lowest possible temperature where a chemical would ignite. Anything above that temperature, it's still going to ignite. So flash point is the temperature where something can catch on fire and very dangerous. The flash point is a descriptive characteristic that we use to describe the differences between flammable fuels like petrol or diesel. In Canada, we call petrol gasoline, but it's all the same. So the flash point, you might hear people talk about fuels that way, like petrol or diesel, but mostly it's used, in my experience, to characterize fire hazards of fuels. Fuels which have a flash point of under 37 degrees Celsius are called flammable. Now, I would know that. You don't have to remember the number, but just know that the term in when you're doing a WHMIS course or occupational health and safety course, when a chemical is called flammable, it means it can ignite at 100 Fahrenheit or around 40 degrees Celsius. And I really want you to think about that in Qatar, in the Middle Eastern context, because in Canada, a lot of the oil and gas is offshore in the Atlantic Ocean, very cold, or northern Canada, where, I mean, it's snowing right now. There's snow. So in Qatar, however, in the summer, not most of the year, but a few months of the year, the temperature outside is over 40, which can be a very dangerous situation when you're dealing with flammable fuels. They can all be readily ignited. So that's why we keep fuels, flammable fuels like propane in, safety tanks that have like pressure valves and they're all, enclosed very tightly in metal. All right. So flashpoint testing, because this is such a big safety issue, and it can talk about you can use it to talk about fuel sources as well. Flashpoint testing is a requirement in this industry to characterize fuels for quality control and safety regulations when you're moving these products. So Qatar, gigantic exporter of LNG, liquefied natural gas, and flashpoint testing would be done to explain or to define something as flammable. And liquefied natural gas, definitely a flammable substance because at very low temperatures, it can be ignited. So when you are transporting LNG on, say, a boat, which Qatar does all the time, those big giant boats with like the domes on top that keep the liquefied natural gas at a certain temperature and pressure, that's because of the flash point. You probably know more about this than I do, and you've probably learned about it in other courses. But when they ship LNG on those boats, so there's my rough boat, there's these giant pressurized domes. And when you transport LNG for safety, it's under high pressure and low temperature. It's kept cold and under pressure. And that's for safety. Because if it was hot, it's ready to be flammable. Explosion, very dangerous. All right, the finale. I have 3 slides and we're done. I do apologize for today's class. Very boring, but these definitions you will see again. The last one is more of a physics term to me than it is a chemistry term. So you guys would have learned about latent heat in physics. The latent heat is the energy, sorry, let me explain this again. The latent heat of vaporization is the amount of energy it takes to turn a liquid into a gas. Now, in chemistry, we would use the term specific heat of vaporization, but I'm following your course outline, and I think in industry, they might call it latent heat. So the latent heat or heat capacity of vaporization is how much energy it takes to turn a liquid into a gas. The energy or enthalpy of vaporization is related to the pressure. So the pressure, the atmospheric pressure, or the pressure of, say, your fractional distillation setup can alter the boiling point. This is something that you might use in a kitchen, a pressure cooker. It lowers the boiling point of liquids so you can cook food faster under higher pressure. Let me just check the chat, and I'm almost done. And I kind of like physics, but as you can tell, I kind of, when I was in university, I did a few courses and then moved into chemistry. All right, 2 more slides. So just kind of putting this all together, how does latent heat relate to your distillation? Well, think of your fractional distillation column. The heat needed to turn something into a gas is obtained from well, we heat it up using a heating source in the bottom. And the heat necessary to volatilize or turn a liquid into a gas is obtained from the heat released from condensing vapors, replacing that liquid that has been removed. So in a fractional distillation column, often it's kept in an insulated vacuum jacket so that heat loss is minimum. We try to keep all of the heat inside the fractional distillation column so we get even separation. And that was an issue that you could have seen in lab number 5, right? We did that in a fume hood in a glass tube. So a lot of the heat was lost to the atmosphere, and a lot of the vapors condensed over and over. I wouldn't call it a lab error, but it's not efficient, right? When you're electricity costs money. So if you're using electricity to heat up petroleum to separate it, you want to keep as much heat in there as possible because, again, energy costs money. So if you're wasting heat, you're wasting money. So distillation columns have been designed for gasoline refineries. They're multiple stories high. They can separate compounds that differ by only a few degrees Celsius, and they are definitely insulated. You can kind of see here, this is obviously not an industrial distillation column, but this would relate to the insulation, trying to keep that column nice and warm so we don't waste energy. All right, guys, that was a bit of a long class, and I didn't mean for it to be long because we're in a rush. We are not in a rush, but I felt that it would be useful to just get section 5.11 out of the way so we can start 5.12. I really like 5.12. Okay, so I'm going to hit stop record, and I'll ask you guys if you have any questions, and I will mention or talk about the lab as well.